Welcome to lecture 19 of Power System Protection course. So in the last lecture, that is lecture 18, we discussed about the carrier aided protection scheme. What is the importance of this carrier aided protection scheme, and also various options available for this. And finally we saw that the PLCC, power line carrier communication, is the best way to do this, because we need to transmit a low volume of data, that is very small volume of data, that is voltage and current information, to the remote end of the fault location where the fault is happening. To the remote end we need to transmit the data. So therefore a high bandwidth is not required, but the speed matters. The speed should be much more less than the 20 milliseconds. So therefore we found that in case of power line carrier communication, so the bandwidth is less as the carrier frequency is very less, but however the time required by this is around 0.2 millisecond. In fact, it was very suitable for this carrier aided application, for relaying application. And also we have seen in the last lecture the basics of the differential protection scheme and how in fact it operates, how it responds to the under normal load condition, under external fault, under internal fault, right. So all these things we have discussed, and now in this lecture we can see already all these things we have seen. Already we have discussed these things. When the external fault happens and when there is some error, CT ratio error and phase angle error, we can see that what happens. This is your ideal secondary current of CT IS, that is equal to IP by N. N is the CT ratio, and in fact it doesn't happen because of the ratio error and phase angle error. So therefore in the CT1 the secondary current we obtain, that is IS1, that is equal to IP by N1. N1 is the actual CT ratio of the CT1, and similarly it makes an angle, the IS1 makes an angle of theta1 with respect to IS, and we call it phase angle error, right. So already we saw this phase angle error, and similarly for CT2 also the IS2, the secondary current of the CT2, is equal to IP by N2. N2 is the actual CT ratio of the CT2 considering the ratio error, and the phase angle error is theta2 here, which is the angle between the IS and IS2. Okay, so now we can see here the difficulty. The difficulty is that even if for an external fault the spill current will be IS1 minus IS2, and therefore some current will flow through this overcurrent relay, and therefore it will respond to the spill current and circuit breaker will trip. So therefore what we can conclude that even for external fault also your differential relay responds, right, when there is certain error is existing in the CTs. In fact, in practice it is always existing. There are errors in CT ratio error and phase angle error. So let us see in terms of stability issues when there is a through fault that we call the external fault, that is the fault is lying outside the protection region. Then also the differential protection scheme responds, and we can express this in terms of the stability, through fault stability we call it, and also stability ratio. What is this? Let us see. Okay, so now we can see that this is the same circuit before we have shown. This is the external fault is happening outside the protection region. This is your protection region, right, up to this, This is your protection region, so your fault is happening external to the protection region, and therefore there will be some spill current, and hence how we will define the through fault stability. Let us see then. This is your characteristic. In fact, if we will plot the spill current versus the versus the current, that is the flowing in the loop, that is the through fault current, we can say loop current or through fault current. If we will plot it, we can see that as the through fault current will increase, your spill current will gradually increase, and after some time it will in fact cross the IPS, that is the pickup current of the overcurrent relay in the spill path. Therefore, this is your characteristic, this is your relay characteristic, right? This is your relay characteristic. Okay. Now, when the point where your through fault characteristic or external fault characteristic is crossing the pickup current or the relay characteristic, that point in fact the critical point, and here we can decide this is the through fault current which is passing through the CTs, and we call it under which the below which the differential protection scheme gives a stable operation, and beyond this point, as soon as the through fault current becomes greater than I stab, this value, then your differential scheme becomes unstable, right? So therefore, this is your stable region and this is your unstable region, right? Unstable. So now now if we will see the stability ratio can be defined as the maximum through fault current beyond which the scheme maloperates. That means this is the maximum current, that is I stab. Okay. So this I stab is the maximum current beyond which your differential scheme or differential relay maloperates, it becomes unstable, and divided by the minimum internal fault current required for tripping. What will be the minimum internal fault current required for the tripping? Let us see what will be the. So this is your internal fault characteristic. If you will plot your internal fault current, then your spill current will increase suddenly, right? It will increase suddenly with a stiff slope. So therefore, it will be a straight line and internal fault characteristic. So where it is crossing the relay characteristic, this point will give us the minimum, in fact we call it minimum internal fault current required for tripping. So this is your IF internal minimum. So that means this is the minimum this is the minimum internal fault at which the relay is tripping, right? Okay. So therefore, stability ratio is defined as the maximum through fault current beyond which the scheme maloperates divided by the minimum internal fault current required for tripping. So that means it is your I stab divided by IF internal minimum, right? So this will give us the stability ratio. That means your stability ratio, if it is higher, it is greater, right? If it increases, the value increases, that means it is good for the differential protection scheme. That means your differential scheme is more accurate. If your stability ratio is less, right, it is decreasing, it is less value, having less value, that means it is responding the through fault or external fault very quickly. That means it is becoming unstable very quickly for the external faults. So therefore, when the stability ratio value becomes more, your differential protection scheme is more stable. That means the through fault stability is enhanced when the stability ratio is more, right? Okay, we'll talk more about this, how to overcome these situations. So again the question is how these characteristics found. This is a very straight line, and this is very this is a very exponential curve, right? The external fault characteristic. How we can obtain this? Just by considering the CT ratio error and the phase angle error, we can find this. Let us see the magnetization curve of the CT and other aspects, then we can very easily understand how we can obtain this. So differential scheme considering CT equivalent circuit. Let us consider the CT equivalent circuit, and then we analyze the differential scheme. So this is your CT, right, where the primary side the number of turns is very less, in fact it is 1 sometime, and on the secondary side the number of turns is very high. So therefore the CT ratio, the ideal CT ratio is, that is IP by IS is equal to N, right? So this is your ideal condition. Now under practical situation, what happens? This is your ideal condition, right? Here the current is entering at the dot, and your current is coming out from the dot at the secondary side. And now we can see, if we'll consider the equivalent circuit parameters, this is the primary side parameters referred to the secondary side, that is I primary dash, L primary dash, and similarly R secondary and L secondary. They are the resistances of secondary side winding and the leakage inductance of the secondary side winding. Similarly, your L mag and R mag, they are the magnetizing resistance and magnetizing reactance, magnetizing inductance of the CT, right? Now we can see that here the current will be IP by N at just after the just in the secondary side winding, when we are considering the ideal transformer, right here. And then after it passes through the magnetizing branch. So in the magnetizing branch, let us say the current is IO. So therefore the net secondary current will be IS, which is actual secondary current which is flowing in the burden. So burden is nothing but relay plus, this is the resistance or impedance of the relay plus pilot wire, right? Okay. So the wire connecting to the relay. So therefore your secondary current flowing through the burden IS will be equal to IP by N minus IO. IO is the magnetizing current which is flowing through the magnetizing branch. And in fact this IO will depend upon this voltage, right, B secondary, which is across the magnetizing branch, and this V secondary will in fact depend upon the current flowing through the burden, right? Okay, so therefore finally your IO also depends upon the burden, right? Okay, so then let us see what happens when V secondary will increase, your IO will increase, then your IS will decrease. Okay, so let us see then the magnetizing characteristic or magnetizing curve of the CT core, right? This is, if you plot the CT secondary voltage versus the magnetizing current, then we will find a voltage like this, the curve like this, right? Okay, so as we increase the magnetizing current up to the knee point, it will be fine, it will be approximately linear, then after that it saturates and very quickly the magnetizing current increases. So therefore we will see when this voltage, this V sec secondary voltage will increase up to this point, the the magnetizing current is fine, right, it is up to this. Then as soon as it go beyond this knee point, this voltage little bit increased, the magnetizing current becomes very huge, right. So very large increase in the magnetizing current happens because of the saturation, and therefore your IS will decrease very drastically, right. Okay, so your IS will decrease drastically, and it is because of this. So therefore magnetization has the impact, and we don't know the CT, whatever CT we consider at both end of the differential relay, we don't know the magnetization characteristic, and sometimes it changes also, these magnetization characteristics as the time passes, right. So therefore we can see here a differential scheme in fact which considers the CT equivalent circuit at both ends. This is the equipment under protection, right, which is protected by the differential scheme, and both the ends we have two CTs connected with ratio n:1, but somehow the magnetizing current here in the CT1 will be IO1, and here it will be IO2, and therefore the net current flowing through this wire, pilot wire, will be IP by N minus IO1, and here it will be IP by N minus IO2. It is for the external fault we are considering, right, and your spill current will become IO2 minus IO1. If we will take the difference of these two currents, IP by N minus IO1 and IP by N minus IO2, then we will see that the spill current will be IO2 minus IO1. They are the magnetizing current of the CT2 minus magnetizing current of the CT1. So we don't, therefore we cannot match exactly the magnetizing current of the CTs which are connected both sides of the equipment in the differential relay. So therefore there will be always spill current flowing because of the through fault, because of the external fault, right. So this is your pilot wire, right. Okay, so now how we can avoid this kind of situation when there is an external fault? Can we reduce this spill current, or can we? So it is possible to do it by just introducing the restraining coil. Suppose we have in this relay we have one operating coil, right. Okay, so it is because it is overcurrent relay, so it has only operating coil, right, that in fact activates because of the current flowing through this, right. Sorry, operating coil, right. And if you can add here one restraining coil which will restrain when there is an through fault current. When the through fault current is increasing, it will restrain more and more. That means it will give an opposing torque more and more. So therefore it will not operate. This relay will not operate. That means under through fault the spill current will be there, which will operate the disc because of the magnetic flux produced in the operating coil. But if we will put a restraining coil which is in fact producing the flux proportional to the circulating current here, that is in fact directly proportional to the through fault current, and that flux, if that flux will produce a restraining torque, then obviously it will balance the operating torque and restraining torque, and gradually the net torque will become 0. So in fact we cannot make the net torque 0, but we can reduce the impact of through fault current or external fault current, right. So how can we make it? So that is why the concept of percentage differential relay came into picture. So what is this percentage differential relay? So, the simple differential relay can be made more stable if somehow a restraining torque, as we discussed, a restraining torque proportional to the through fault current could be developed. Okay, already we discussed this, and then the operating torque still being proportional to the spill current, but there will be the restraining torque which is proportional to the through fault current. Therefore, it will oppose the operating torque produced because of the spill current, right. So, now we can see here in this diagram we have two CTs, and here we have the relay, right. So, this is your percentage differential relay, which is having one operating coil having the number of turns NO, and we have restraining coil which is having the number of turns NR, which is in fact put in two halves, divided in two halves and put in two different sides, like right side and left side of the operating coil. So, the NR by 2 and NR by 2. So, now through the spill path the current is I1 minus I2, and which in fact activates the operating coil, and in the restraining coil the current passing through is I2 here, right, in NR I2, and here it is I1, right. So, therefore, both the coils will produce a restraining torque, right. Now, we can see a simple balanced beam structure of a differential relay, right. Here it is your operating coil, and here we have restraining coil, and as soon as there is a current flowing through this, so this is the spill current flowing in the operating coil, and this is your circulating current flowing through the restraining coil, and there is a spring. So, this operating torque will give a downward force, and the restraining torque will give also a downward force, right. So, therefore, it will give a restraining force, right. So, when there is a through fault, because of this restraining force, the strip contact will not be sorted. When there is an internal fault, only the operating coil will be activated, and therefore, these two trip contacts will be short circuited, right. Okay. So, this is a basic balance beam structure. Similar principle can be applied to a disc, aluminum disc or electromagnetic relay, right, which is consisting of aluminum disc. Already we talked about discussed these things in your overcurrent relay. So, let us consider the analysis of this percentage differential relay. So, what will be the Ampere-turns acting on the left hand section of the restraining coil? Already we have seen, and that will be nothing but NR by 2 I1, right. And similarly, the Ampere-turns acting on the right hand side section of the restraining coil will be NR by 2 I2, already I told this, and total Ampere-turns acting on the restraining coil will be NR by 2 into I1 plus I2. Okay. Now, noting that torque is an electromagnetic in an electromagnetic relay is proportional to the square of the flux, therefore, it will be also proportional to the square of the MMF, right. So, therefore, the torque produced by the restraining coil will be proportional to the square of MMF. MMF is your NR I1 plus I2 by 2 square, and M is your constant of proportionality. Restraining torque produced by the control spring will be, let us say, T spring, and total restraining torque will be how much? It will be total restraining, because the restraining torque is also exerted by the spring, T spring. So, therefore, total restraining torque will be M into NR I1 plus I2 by 2 square whole square plus T spring. This is your net restraining torque, and your operating torque will be the same M. M is the constant of proportionality, and the MMF in the operating coil is NO into I1 minus I2 whole square, right. So, MMF in the operating coil will be NO I1 minus I2, and square is taken because the torque is directly proportional to the square of the flux. So, here the square of the MMF, right. Now, if we will neglect the restraining torque due to spring, suppose we are neglecting the restraining torque due to spring. Now, what will happen, the equation, both equation if we will equate under the verge of the operation. So, just starting point of the operation, then your operating torque will become equal to the restraining torque, that is M into NO into I1 minus I2 square whole square equal to M into NR I1 plus I2 by 2 whole square. So, from this equation we will find that I1 minus I2 equal to K into I1 plus I2 by 2. So, K is nothing but your NR by NO. Okay, this is your constant, and NR is the number of turns in the restraining coil, and NO is your number of turns in the operating coil. So, however, if we take into account the effect of the control spring, the above equation can be written as this, right. So, if we will again consider the control spring into account, also from the beginning you can derive, and you will find a constant, and that constant we can represent at KO. So, therefore, I can write I1 minus I2 equal to K times I1 plus I2 by 2 plus KO. So, KO is, it is due to the spring, okay, due to effect of spring, effect of the control spring you can say, right. So, it is just, you can put it here, this effect of control spring, where KO accounts for the effect of spring. So, now let us see the different characteristics, right. Okay, so let us see the characteristics here. If we will plot the spill current versus the through fault current, that is nothing but I1 plus I2 by 2, this is in fact average through fault current, right. Now, if we will plot the external fault characteristic, it will be exponential, as we know, right. As your external fault current will increase, suddenly it will become very high, the spill current will become very high because of the magnetizing, increase in the magnetizing current, right. It is because of the increase in the magnetizing current, because the core of the CT becomes saturated during high through fault current, right. Magnetizing, increase in the magnetizing current, right. And your internal fault characteristic will remain as a straight line. Why it is remaining straight line? Because for small internal fault current, your spill current will be high, right, and therefore your overcurrent relay will respond to this spill current, and therefore your core, CT core will never become saturated for internal fault condition. For external fault condition, it will become saturated, and therefore suddenly it is increasing exponentially, the spill current will increase here, right. Okay. So, therefore, this is your external fault characteristic, this is your internal fault characteristic, and this is what will be the slope of this internal fault characteristic, we will see that, and this will be your characteristic of the percentage relay, a percentage bias relay, right, differential relay. So, this is under certain slope. So, how we decide the slope, or let us see those things. So, for a single feed line with internal fault, let us consider the internal fault for single feed line. So, your I2 will become 0 and the spill current will become I1 minus I2, that will be equal to I1. So, spill current for internal fault condition for a single feed line, it will become I1, right. Now, the circulating current will become I1 plus I2 by 2, because I2 is equal to 0 here, right. So therefore your I1, it will become your circulating current will become I1 by 2 under internal fault condition, and therefore your if we will see your slope will be how much? Your slope will be how much here? It will be I1 by 2, it is 2, right? So it is nothing but 200%. So therefore for internal fault we found the slope is 200%, right? Okay. And for different percentage bias we found this characteristic, and this is for 25% slope, this percentage bias is considered, right? So this is 25%, this slope is 25%. So the stability ratio already we know that is IF max external divided by IF min internal, right? Okay. So now we can see, if we will compare the previous condition, previously our differential relay characteristic is this dotted line, right? This is the simple differential relay characteristic, this dotted line, and now your improved or your percentage bias differential characteristic is this, which is having the slope of 25%, 0.25, right? So now if we will compare the stability ratio for these two characteristics of the relay, one is for the simple differential relay and other one is for the percentage bias differential relay, then now we can see that the stability ratio is much more enhanced for this percentage biased differential relay, right? Okay, much more enhanced as compared to the simple differential relay, because for simple differential relay your external current IF maximum external will be here, right? Let us mark it as IF max 1, right? And here for your percentage bias differential relay, your IF max external will be, let us mark it IF max 2, and your IF max 2 is greater than IF max 1, right? It is much more greater, and your IF min int will be here, right, where your internal fault characteristic is a crossing or making cross section with this, and there is not much difference between the IF internal, IF minimum internal, right? Very small difference. So therefore it is approximately, we can say that IF min internal will remain same for both the characteristic, for the simple impedance relay and for the percentage differential relay, right? So it will be approximately same, right? So therefore now if we will calculate the stability ratio for both the relays, for the simple differential relay and for the percentage differential relay, your stability ratio will be much more enhanced. For stability ratio is much more enhanced for your percentage bias relay, right? Percentage bias differential relay. As we can see from the characteristic and calculating the stability ratio, we can easily observe this, right? Okay. Let us see how the characteristic for a percentage differential relay is obtained. We can see here, this is your characteristic, this straight line with an intercept here is the characteristic for the percentage differential relay, right? How it is obtained? It is in fact obtained from this equation, right? If you will see, this is the equation by which this is obtained. We can see here the spill current I1 minus I2 is plotted versus I1 plus I2 by 2, which is the through fault current, right? And K0 in fact, which is the it is because of the effect of the spring, this gives the intercept, right? Y-axis intercept, and the K in fact gives the slope. So this slope is decided by the K, okay. So this is the slope is decided by K. So K is nothing but equal to NR by NO, right? So therefore, based on the number of turns in the restraining coil and number of turns in the operating coil, we decide the slope of this percentage biasing. So similarly, if we want to increase the slope of this curve, slope of this straight line, in fact this is not touching the not touching the simple differential relay characteristic, so it is just shown like that, but the intercept may be here, right? So the slope can be increased just by changing the number of turns in the restraining coil and changing the number of turns in the operating coil. If you want to increase, if we will increase the number of turns in the restraining coil, we can increase the slope, or decrease the number of we cannot in fact change the number of turns in the operating coil, but we can adjust the number of turns in the restraining coil. We will see in the next slide how we can do that. So now we will see the block diagram of percentage differential relay, how it in fact acts, right? How we in fact set the slope of the percentage bias differential relay. In fact, we can see in this figure, if we can increase the slope, suppose we will make 40%, it will become like this. So again your I stability will increase, and by that way again it increases the stability ratio, right? So as your slope will go on increasing for this percentage bias differential relay, your stability ratio also will increase, right? So as your slope is increasing for the percentage bias differential relay, your stability ratio will also increase by enhancing the stability or stable operation of the differential relay. Right, so let us see the block diagram of the percentage differential relay, how it looks like. So this is your restraining coil. The restraining coil has taps, different taps. So when we choose certain taps at both the side, it will give certain slope, right? So for tap 1, it will give 20% slope. For tap 2, it will give 30% slope. That means it is more restraining. And for tap 3, it is 40% slope. Like that, you can increase the slope gradually when we will move the contacts to different taps, right? And your NO is your operating coil, and it has two set points. One is your pickup current set point, and other one is your slope adjustment set point. We call it percentage biasing adjustment, right? So it has two set points, okay. Like in case of overcurrent relay, we have one set point only. We have to set the pickup current. But in case of directional overcurrent relay, we have in case of overcurrent relay, we have two set points. One is your time of operation, delay time, and here the operating current or pickup current. But in case of directional overcurrent relay, we have three set points. One is your MTA, right? That is your torque, maximum torque angle, and your current, pickup current, and third is your delay time. Similarly, here in case of differential relay, we have two set point. One is this is for your instantaneous percentage differential relay. One is your current set point. We call it current, that is I pickup, okay. And second one is your percentage bias setting. Okay, so this current setting we can do it by adjusting the spring in the relay, and this restraining, this percentage bias setting we can do just by adjusting the tap position of the restraining coils, right? Okay. So now this is all about your percentage bias differential relay. Now I will talk about little bit earth leakage protection. So when there is equipment under protection, differential protection scheme, and suppose its body touched to the ground, suppose some insulation breakage happen, then how we can protect this? This is called earth leakage protection. So many times because of insulation failure, the chassis of the equipment becomes live, right? It remains live as soon as we touch. So the current passes through us to the ground, right? So this causes a leakage of current to the earth from the chassis, as the chassis is always connected to the earth. Okay. However, the leakage current may be too small for an overcurrent relay to operate. This poses danger to the personnel who come in contact with the chassis. So even if it is very small current for the overcurrent relay to operate, but it poses danger to the personnel who come in contact. So therefore, a special type of differential relay known as earth leakage relay or current balance relay, we call it earth leakage relay or current balance relay, can easily detect such faults. So what is the structure of this fault of this relay? In case the chassis of the equipment is not earthed, the relay will not trip because of the leakage. So it should be earthed. If it is earthed, then the relay will detect the leakage current and it will. So this earth leakage protection, let us see for single phase load, single phase connection for. So now this is your core, iron core. We call it toroid generally, right? So this is the iron core on which there are two coils. They are put on this core in such a way that the flux produced by these two coils, that is coil A and coil B, will be opposing to each other, right? So in the current, because we know in single phase we have a phase wire and other one is a neutral wire. So phase wire is the current where the current is passing through the phase wire and it returns via the neutral wire to the source. Now we can see that the flux produced, if there is no leakage here, when these currents will be same, right? IPH will be equal to IN. So therefore the flux produced by these two coils, coil A and B, will be equal and opposite. So therefore there will be no voltage induced in the coil C, which is connected to the overcurrent relay. So therefore there will be no current also through the overcurrent relay. So therefore it will not respond. But as soon as there is a leakage current, okay, let us say the leakage current is I leak, and now the current pass through this will be, it will be IN will become IPH minus I leakage, right? Okay. So now your then your flux here will produce, the net flux produced in this toroid will have some impact, and it will produce an EMF in C, coil C, and therefore a current will pass through this overcurrent relay, right? So that by that way it will in fact operate, the overcurrent relay will operate, and it will somehow it will trip the breaker or whatever the switches are connected, right? Now this arrangement is valid for a single phase connection. Now we will see the earth leakage protection for a three phase load, three phase connection. So suppose we have a three phase load here, we can see here we have a three phase load and it is supplied by a three phase supply. And now if we have a similar iron core and it is being coiled by this, it is being, the one coil is put which is connected through the overcurrent relay, connected through the overcurrent relay, and let us see what happens when the balanced current will flow through this under balanced condition. That means it will produce no flux in the core. So net flux produced in this core will be 0, because the net current passing through this coil will be this core will be 0, right? Because we know IA plus IB plus IC equal to 0 under balanced condition, right? This is under balanced condition, and so therefore the net flux will be 0, and therefore there will be no EMF induced in this coil, and the current through the relay will be 0. So, as soon as there is a leakage current through here somehow because of some insulation breakage, then this becomes unbalanced, and Ia plus Ib plus Ic will become not equal to 0, right. So, it will become now not equal to 0. So, some current will flow through this and through this core, and therefore, some flux will be producing in this core, and which in fact produce the flux in this coil, and hence the current, some current will pass over through this relay. So, these overcurrent relays are in fact very sensitive, they very quickly they sense even a small current flows through. Right. So, this is the case. If suppose now if your supply or load becomes unbalanced, then under that condition what happens? Then there will be a neutral current, right. Unbalance means if there will be no neutral wire here along with this 3-phase wire, then your net current will not be 0. So, there will be some flux, in this core, and that will produce an EMF. But if we'll change little bit the arrangement, if we'll put the neutral wire along with these 3-phase wires, now under unbalanced condition also it will become Ia plus Ib plus In will be equal to 0, right, because In is always a return path when there is unbalancing, right. So, therefore, it will become 0, and hence your net flux in the core will be 0, and there will be no current. So, therefore, it is the safest condition is we should put one neutral wire along with the 3-phase wire, which is connected to the neutral of the load to the neutral of the supply. So, by that way we can this is also a differential protection scheme, right. So, this is the earth leakage protection of 3-phase load. Okay. So, we will see more about the application of the differential protection schemes in transformer, in our bus bar protection, right. So, all these things we will see in the next class onwards, that is in lecture 20 onwards. So, thank you very much for your kind attention. Thanks a lot.